We're going to look at some examples of composition of functions. So maybe you've seen some examples of polynomial ones. I want to look at some that are a little more involved. So in this example, I have the polynomial function x squared plus x, and the rational function g of x equals x over x plus 2. I'm trying to find f of g of x, which of course is the same as f composed with g of x. So recall, when you do something like this, you're going to replace the g of x with the g of x function. So the x values in the f function are going to be replaced with the g function. So the f function is x squared plus x. So I'm going to actually put the g function inside those x values. So the x over the x plus 2 gets put in the place of those x's. And then I'm going to work those out. So notice with this first one, I have to have x over x plus 2 squared. Order of operations tells me that I do that first, that I do the exponents first. So x over x plus 2, I multiply the numerators to get x squared, and the denominators to get x plus 2 squared. So I may want to leave it like that, but if I want to get one answer, one fraction as my answer, I would need to go ahead and get common denominators. So if I was going to get to common denominators, I need to multiply this one by multiplication. So a solid dot, we're learning that the circle, the open one, is composition. The solid one is multiplication. So then I would have x squared over x plus 2 squared plus x squared plus 2x. So I'm distributing that to get the x squared plus 2x over x plus 2 squared. I can then add the like terms here. So 2x squared plus 2x over x plus 2 squared. Notice if I did the reverse, I would get something a little different. So when I did f of g, I get 2x squared plus 2x over x plus 2 squared. If instead I do g of f, so g composed with f of x, which would be g at f at x, I'm going to start with the g function, which has x over x plus 2. The g function is x over x plus 2. What I'm going to put in each of these is the f function. The x squared plus x is going to go in each of those. So the only simplification I can do here is to write this as x squared plus x over x squared plus x plus 2. Not quite the same answer that I got when I did f of g. Okay, let's look at one that has a square root in it. Let's get the example where we have f of x is the square root of x plus 3, and g of x is 2x minus 1. So let's do both of them. f of g of x, or f composed with g of x. So I'm going to start with the f function, which is the square root of x plus 3. But instead of the x, I'm going to put in place of the x, the g of x, but the g of x is 2x minus 1. So I put that inside of it. And I get the square root 2x minus 1 plus 3. So that is the 2x, square root of 2x plus 2. Now if I were to do g composed with f, or g of f of x, I would start with the g function, and in the place of the x in the g function, which is 2x minus 1, 2x minus 1, I'm going to put the radical. The radical is the f of x, the x plus 3. Since there are implied parentheses inside a radical, there is no need for these outer parentheses, and I can just write this as 2 square root of x plus 3 minus 1. Now, can I do a function composed with itself, such as g of x? Sure. I can do that. Means I'm going to start with the g function, which is 2x minus 1. And what am I going to put in the place of that x? Well, remember, g of x is 2x minus 1. So in place of the x, I'm going to actually put 2x minus 1. So I can now work this out by distributing. So that's going to be 4x minus 2 minus 1, or 4x minus 3. Could I do the f with the f? Sure. The square root of x plus 3 plus 3. Or the square root of x plus 3. Looks kind of strange. Whoops. Sorry, got that off of there. The square root of the x plus 3. So I replace the x with the square root of x plus 3. I don't really need the parentheses, so it's the square root of x plus 3. Right? I think I have another one here, which is so simple it's hard. So to do f composed with g is not hard, because in this case the f function is 5x squared plus 3. So in place of the x, I'm going to put the g of x function, was as a constant function, it's just 8. So I know that 5 times 8 squared requires that I do the 8 squared first, order of operations. Please excuse my dear Aunt Sally, exponents first, so that's 64. And then I got to do the 5 times the 64. 5 times 4 is 20. 5 times 6 is 32. So that's just going to be 323. Here's the part that's so simple it's hard, doing the g of f. G of f of x. So I'm going to copy the g function, putting a parentheses wherever I see x. I don't see any x's, so I don't put any parentheses. So the answer is just 8. Notice that g at anything is 8. And if I were to actually graph this, it would just be a straight line at 8. So if it's a constant function, the answer is the constant value. That doesn't change. All right, let's look at this last special one. And let's try f composed with g, which is the same as f of g of x. So I'm going to take the f function. So that's 2x minus 3/5. And I'm going to put in it the g function, 1/2 x plus 3/10. So what I need to do is distribute the 2, if I distribute the 2, I get 2 halves, or 1x, plus 2 times 3, which is 6/10. 6/10 reduces to 3/5. And then there's that minus 3/5. Those two cancel out, so I get x. Whenever you compose two functions and you get x, they're special functions. So if you compose two functions and you get x, f and g, or you could say f of x and g of x, are inverse functions. So you'll probably be learning about inverse functions very soon if you've been looking at composition. Okay, there's some examples of composition.